morning and welcome back. So the topic this week is about density matrices, which we started to scratch the surface of last week, and then belt states and the concept of entropy. So all these topics which we are going to deal with today are background topics which will enter into the work which we're going to do on project number 1. But there's also background information which is important for understanding what we end up doing in quantum computing and quantum machine learning later. Now, so the topic which we will begin with is actually a quick reminder about some of the states, the 2-qubit states, which we looked at last week. Now, if we get time, we will also get started with gates and more, although this is a topic which will be the main focus for next week. And next week is also the week when we will start in more detail to discuss project number 1. And next week, we will also introduce some of the basic Hamiltonians, which we're going to look at, which we will reformulate in terms of Pauli spin matrices, which then paves the ground for starting with standard quantum computing algorithms for finding the eigenvalues of a given Hamiltonian using the variational quantum eigensolver, which is going to be the main algorithm we will study in project 1. However, today, and as we did last week and the week before, we need to bring in some of these basic concepts, in particular the concept of entanglement, which is going to play a major role also when we are going to make so-called parameterized quantum circuits in order to implement a variational quantum eigensolver, which is one of the more efficient algorithms for solving eigenvalue problems and simulating Hamiltonian systems on a quantum computer. Now, the reading suggestions for this week are taken from a textbook by Olivares, which you have access to. Or if you wish to dive more into the mathematics of quantum computing, Scherer's textbook contains many of the derivations behind density matrices, entanglements, and entropy, etc. So the material is something you find at the usual place. You can click on this one, and you will also find the exercises. If you go to the same folder with the week 3 PDF, there you will find also the exercises for this week. These exercises are also meant to be discussed next week. So the exercises from the previous week, the exercises in the slides from the previous week are those which we will be discussing today. And the exercises you find here are actually meant for next week. But if you feel you'd like to jump into it, take a look at the exercises and try to look at them before you look at the solutions, which are also included in the same weekly slides. So if we now move on a little bit, I just wanted to give a quick motivation for why we are going to look into these quantities. So what we are going to do is to study entanglement and study its importance when we are running quantum simulations and why this is such a central feature. And we are going to use the 2-qubit system, which we discussed last week, where we had a simple computational basis. And the computational basis, which we described then, was also used to define a new computational basis, which are the so-called belt states, which are entangled states, and which we discussed last week. So if you want to remind yourself a little bit about what the belt states are, you will see a discussion today. But I recommend to take a look at the lectures from last week because we discussed that in more depth then. And these two quantities, the concept of density matrices applied to these belt states and discussions of entanglements, and together with technicalities like the Schmidt decompositions, these are actually important quantities in analyzing many of the quantum computing examples to come. The Schmidt decomposition, which we will mention next week, is also a linear decomposition which allows us to express a vector in terms of a tensor product of two inner product spaces. And in quantum information theory, quantum computing, it is widely used to define and describe entanglement. So we will discuss that next week. So a quick reminder on the density matrices and traces. So I'm going to use slides, and then when needed, I will jump into the whiteboard for some further details, or the Jupyter Notebook when we're going to run some code examples. So you will also find the companion Jupyter Notebook when you go to the public domain of the GitHub address. So we have the spectral decomposition, which we defined last week, where we have a computational basis, where this basis here can be an eigenbasis of a specific operator. And then we can expand this operator in terms of the eigenvalues and the eigenbasis, which we obviously have assumed is orthogonalized and normalized. Now, similarly, you can express an operator or given function A, which is then given by the function as a function of this operator in terms of this computational basis. And just a quick reminder, and this was one of the exercises we looked at last week, the trace of product of matrices is cyclic, and that means we have this relation here, which is going to come pretty handy when we are going to calculate traces. So that means that when we take the trace of this quantity here, of A acting on these states, we can actually look at that one as the standard expectation value, because we're using the property that the trace is cyclic. And psi, the outer product of psi is a matrix, and A is now an operator which is acting on that matrix, which means either a vector or a matrix. And then when we use the spectral decomposition, we defined also the density matrix, where P of I is the probability in being one of the states I here. And these are the eigenvalues of the density, which is then linked with the orthogonal basis which we have. And the trace of the density matrix, as we also saw last week, is equal to 1. So this is one of the quantities which we will play around with. It is invariant under unitary transformation. So we have a unitary operator given by these matrices U here. We know that the matrices, if this is a real matrix, then we just look at the transpose. But this is just the standard Hermitian conjugate, and that has to satisfy this relation which you see here, which most of you are pretty familiar with. And that means that if I now take perform a unitary similarity transformation of the density matrix, I can actually rewrite that one as this operation here. And if I take the trace of that quantity, then the trace is simply us taking U times rho times U Hermitian conjugate, and using the cyclic properties of the trace, then we can rewrite this simply as U times U Hermitian conjugate times rho. And this quantity here is just equal to the identity matrix multiplied with rho. So that means that if, since we have defined the trace of the density matrix to be equal to 1, this quantity here is simply equal to 1. So that means that the trace, this is a very important property, the trace is actually conserved under unitary transformations. So let's just remind ourselves of the Bell states, because this is also going to pave the way for the first parts of project number 1, where we are going to encode 1 qubit state and 2 qubit states. We're going to perform operations on the so-called Bell states. And then based on that one, we will be calculating quantities like the entropy, the so-called von Neumann entropy. We're going to study entanglement and basic properties of these quantum mechanical systems. So the basic states which we started with as a computational basis, this is also what we'll label as a classical basis. There is no quantum mechanics here. This could just be a way of expressing bit 0 and bit 1. And we have 2 systems, 2 subsystems, A and B. So you could think of you having 2 harmonic oscillator wells, and in each well there is 1 particle, could be an electron with spin up and spin down. And the states of the electron, spin up or spin down, could then correspond to bit 0 and bit 1 for system A and system B. So the subsystems could represent single particle states, or they could actually be composite many particle systems of a given symmetry. Then what we did, and this is also a reminder from the previous 2 weeks, the first 2 weeks, we can then construct a many-body computational basis states, which are now defined by a 2 qubit system. And we normally, and this is again a reminder from last week, we would use this more compact notation, and later we're just going to replace the 0, 0 with just a number, which we can deduce from a bit representation. And we have in principle the tensor product between the bits in system A and system B, and that gives us a vector of length 4, as expected. Since we have 2 vectors of length 2, that has to lead to a vector of length 4, obviously. And this is the new computational basis, and it's pretty easy, and we had that as an exercise to show that this is an orthogonal basis. Now then, what we did was to construct the so-called Bell states, which are our first examples of an entangled basis. So what we have now is different states which also give us an orthogonal and normalized basis. It's easy to see that these states are normalized. This is actually one of the exercises. And this is a state which cannot be written as a product states of 0, 0, 0, 1, 1, 0, and 1, 1. So this is our first encounter with what we call an entangled state. Last week, we saw an example of an entangled state from a modeling of a realistic system like the helium atom, where the spin degrees of freedom in the ground state ansatz for the helium atom then defined an entangled states, because we cannot write the spin part of the wave function as a product state of 2 independent single particle states. Whereas 0, 0 and 1, 1 separately, these are just product states as we have defined here. So these are the Bell states, and it's quite easy to convince yourself that these states also form an orthonormal basis. And these are the states we're going to play around with a little bit now. So when we then perform a measurement on this system, if we take one of the above Bell states, this automatically determines, as we'll see below, the state of the second qubit. And this is a very interesting property. So to convince ourselves about this, let's now assume that we perform a measurement on the qubit in system A. So what we're going to do now is to introduce the projections with outcomes 0, 1. So you could think of the outcome 0. When we measure on the first qubit, this is just given by the projection operator. And since it's not doing anything on qubit 2 in system B, we have to tensor product that one with the identity matrix. So the identity matrix here is a 2 by 2 matrix. And we know that the projection operator, which now acts on the qubit in A, system A, is simply given by the outer product of the 1 qubit state 0, 0, which is then given by this one, this matrix here. And then when we take the tensor product, this gives us an operator now, which is simply defined by this matrix. And you see now that since we only have ones on the first, on the top here, this is the part which will actually act on the first qubit. And you can see that if you go back to this state here, you see now that it acts only on the first qubit, which is here, which would be this one if you act on 0, 0. And it also, when it acts on the second one, it will actually be acting on this system here. So it's actually pretty easy to see when you apply this matrix to one of these computational basis states, you will see that that actually acts on the first qubit. And similarly, I can do the same thing when I project out the second state. Then I will be projecting out the qubit state with 1. And then you see now that this acts only on the parts which will include the first qubit in the 1 state here. So for the projection of the system A, we would then have these 2 matrices. And when we apply these 2 matrices to the one of the Bell states, you see now that the only thing we have to do now is simply to calculate the expectation value here. So we are projecting out the state 0 in the first qubit, and then, or the system A, and that gives us simply a factor of a half. And similarly, if we do that with the state with the qubit 1, then we also get a factor of a half here. So this is pretty straightforward to set up. So after the measurements, which we have done, we would have the wave function in the new state. So that means that we have a normalization factor, 1 square root of 2 here, which we have to take into account. And then we simply perform the operation here. We calculate the projection, and then we have the state, the new state, which then projects out qubit 0. So we are left with the state 0, 0. If we take the projection on the qubit in the state 1 in system A, then what we get is simply 1, 1 here, which is the other component of the Bell state. So what we see from these equations is that the state of the second qubit, which is this one or that one, is actually determined even though the measurement has only taken place locally on system A. And this is a pretty remarkable property. So if we, on the other hand, if we consider a state like this one, this is a pure product state of the single qubits in system A and system B. So what we normally do is that we call a state like this one a pure product states. So quantum states that cannot be written as a mixture of other states, they would typically be called pure quantum states or just product states, while all other states are normally called mixed quantum states. So this state here, which you see here, is then just a pure product state. And as we will see later, I mean, normally pure product states will just give us zero entanglement because this is not an entangled state. And we can define exactly in terms of the product of independent particles in each system, A and B, and that gives us the final state. So a state like one of the Bell states, where we have introduced the subscript A and B to indicate that the state is composed of single states from two subsystems. This is, on the other hand, a mixed state, and we cannot determine whether system A is in state 0 or 1, because the system A is now, in principle, a superposition of state 0 and 1. And the above state is a superposition of these two states, and it's not possible to determine individual states of system A and B, respectively. So we say that the system is then in a superposition of these two states. So, and we say that the state is entangled, and that yields the following definition of entangled states: a pure bipartite state, psi A or B, is entangled if it cannot be written as a product state of the two subsystems for any choice of the states psi in A and phi in B. Otherwise, we would say that the state is separable, because then we can separate the system. So if you look at these two, the product state here, then we can obviously separate the system into system A and subsystem B. So we also have examples of so-called maximal entangled states, which has also been labeled in the literature as a decay state. And this would typically be defined this one as like this one. So we call such a two-body system or two-state system, two-particle system, or just having two systems here composed of systems A and B. And these systems can be single particle systems or single qubit systems, or it can be actually, if we think of the single qubit systems, they could represent some low-lying states of complicated many-body systems. And with such a system here, we would call it separable if its density matrix can be written out as a tensor product of the individual density matrices. So a separable system, or which also leads to a pure or as we called previously, just to bring back some of the definitions which we had. So a pure product state. That leads to a density matrix, which then can simply be written out as the tensor product of these two respective density matrices for subsystem A and subsystem B. So if we now summarize for these four Bell states, what we have done is to take bits 0 and 1s for the subsystems as our computational basis. And now we skip these subscripts, system A and system B, and we simply use the computational notation here, which is much more compact for the computational basis. And with that computational basis, we can also define another computational basis, which are the Bell states, which form an orthogonal basis. And so these form an orthogonal basis in a system where we have two states in one of the systems and two states in the other ones. And we would simply write this out as these two complex numbers, tensor product with the other two complex numbers. And they're actually eigenstates of correlated observables. And actually, in our case, it's a parity and certain two-qubit Pauli products, which we will come back to later. Now, the density matrix for all four Bell states is then pretty straightforward to calculate. So if we now take the density operator for one of the Bell states, then we can simply write out the calculations of the density matrix. And this just proceeds with us taking into account all the elements which we have. So we need to take the outer product of 0, 0, 0, 0 with 1, 1, 1, 1 with 0, 0, and 1, 1 here. And if we do that, we can continue with the other states. And that is simply something which gives us the similar relations which you see here. And it's pretty straightforward, actually, to set up these outer products and compute the final density matrix. And if we now use this ordering, where we start with 0, 0, 0, 1, 1, 0, and 1, 1, then for the first Bell state, the 5 plus, which we had, this is the corresponding density matrix. And you see now that if I take the trace of the density matrix, you will see that this sums up to 1. So we get 2 divided by 1/2, which gives us 1. And similarly for the other states, this 5 minus will have minuses here. And again, if we sum up the diagonal elements, this is also going to give us 1. And this is something which we see again for all the other states. So these are the density matrices of the 4 Bell states. And it's actually useful to set up a small program which calculates these quantities, because we are going to evaluate density matrices in many of the different exercises for project number 1. So we can also show that they form an orthonormal basis, and then it simply suffices to prove first the normalization factor. And we see that when we calculate the norm of these states, you will see that for all these states here, the norm is simply equal to 1. So if we just take the norm of the different states, we know that this one has to be 0, the second one here, and the third one has to be 0, and then it's only the first and the fourth which give us something which is non-zero. And when we calculate the norm, we see immediately this is equal to 1. And then the inner products between distinct Bell states, they vanish. So if we take this example with the 5 plus and the 5 minus, we see again that when we calculate the inner product of that quantity here, this is simply equal to 0. And you see that by calculating the different terms, because we get a minus in front of the 1, 1, whereas the 0, 0 and 1, 1 and 1, 1 and 0, 0 have obviously to be equal to 0. And it's pretty straightforward to show that. So we will just leave the other one, the other states as exercises. But then the completeness, since there are 4 orthonormal vectors in a 4-dimensional space, that simply leads that they form a basis which is an orthogonal and now normalized basis. So this is pretty easy to see, as long as we assume that since we have 4 orthonormal vectors in a 4-dimensional space, they form a complete basis here. Now, there are some other definitions which are going to be very important for us now when we are going to define whether we have so-called pure states or mixed states. So the density operator, so a quantum state can be represented by the density matrix, which is a positive semi-definite operator, which means that if I calculate the eigenvalues of the density matrix, which is just the outer product of a given state, then we know that these eigenvalues are going to be largely equal to 0, and the trace is equal to 1. So a pure state, the state is pure if, and these are definitions, when we now take and square the density matrix, this is actually equal to the density matrix, and that means also that the trace of the density matrix is equal to 1. So if you go into Scherer's text, you will also see proofs of many of the statements which follow here. We will simply just state many of the properties of the density matrix without going into the proofs. So as I said, Scherer's text, which is an excellent text and contains several of the proofs and derivations, is a text which has a focus on the mathematics of quantum computing. Now, a mixed state, on the other hand, is defined as a state which gives a density matrix whose squared density matrix is not equal to the density matrix. And that means that the trace of the squared density matrix is less than 1. So if I have a maximal mixed single qubit state, that has a typical square density matrix equal to a half. And we are going to see examples with the Bell states, that the Bell states actually do not give us a density matrix, which when it's squared, gives us a trace which is equal to 1. So just to remind ourselves, when we have a so-called pure state, this means that the density matrix squared is equal to the density matrix, and that means that the trace of the density matrix squared is equal to 1. The definition of a so-called mixed state, and we will see immediately now what that means for us, is that we have a density matrix when it's squared, which is less than 1 when we take the trace. So let's now look at an explicit example with the so-called Bell states, and where we are going to calculate the density matrix for one of the Bell states, which we have already found to be equal to 1 when we take the trace of the square density matrix and the density matrix. But then, if we now trace out the subsystem, we are now interested in knowing whether the state is uncertain in the sense that we don't know whether the subsystem is in qubit 0, qubit 1. So we saw that for the full system, when we took the trace, we can actually say that when the trace is equal to 1 of both the density matrix squared and the density matrix, we are in a pure state. So a pure state does not need to be a pure product state, but it can also be a state which is well defined, and we know for certain that the system is in that specific state. And if we know that the system has been prepared in one of the Bell states, we know the explicit state, but we may not know in which state each individual qubit is in. So one of the quantities which we often use then to say something about the degree of entanglement of a given subsystem is whether we can now define precisely if that subsystem is in one of the specific states or on the other on one of the other states. If we cannot do that, well, then we say that the system is in a mixed state. So let's look now at the total density matrix, and this could be one for the so-called Bell states, or any other states which we are interested in. So if we now look at the phi plus state, what we have defined already is the density matrix for the full system, which would then be given by this quantity rho with subscripts A and B. So what we are doing now is that we're going to trace out one of the subsystems so that we have the density matrix only for one of the specific subsystems. So what that means is that when we now are tracing out mathematically subsystem B, it means that if we take one of these states like 0, 0, what this means, so A and C are in subsystem A, and B and D are in subsystem B, then we have the overlap between D and B when we are tracing out system B, and then we have the outer product for the subsystem A. So that means that if I take the traces and trace out subsystem B in this two-body state, which is a two-qubit state for the phi plus state, then we get the trace of B for 0, 0 with 0, 0, which simply becomes 0, 0 here. And this is for subsystem A. So for the two intermediate ones, we see immediately then that this leads to zeros, because these states are orthogonal to each other in a one-qubit basis. And then for the 1, 1 with the 1, 1, we simply get the outer product of the two one-qubit states in system A. So let's take a closer look at this when we now set up the basic matrix operations for these tracing out of subsystems. So let's now switch to the whiteboard shortly. So what we are interested in now is the density matrix for the subsystem. And what we want to use this density matrix for is to say whether we can precisely define that the system, the subsystem, is in either qubit 0 or qubit 1 for our specific case. So what we are interested in now is the density matrix for subsystem A, which is then defined as the trace over subsystem B, and then we have the density matrix for rho of A and B, the total system which we have. So this means that what we have then, if we use the definitions, so we should then have the overlap between the qubit 0 in system B with the density matrix AB and qubit 0. So this is essentially what we end up calculating. And then we have qubit 1 and then rho AB and qubit 1 in system B. This is when we are now tracing out the subsystem B because we are not interested in those degrees of freedom. Now, there's an alternative to this. And for those of you who are familiar with statistics, we have a quantity which is called the marginal probability. So let me just set up that as a kind of small digression here, because this may be something which gives us a link with a topic which is familiar to many of you. So suppose now that we have a probability which is given by two variables, x and y. So this is a total probability. Now, one of the things we often are interested in is just the probability for one of the variables. And that leads to the so-called marginal probability. And the marginal probability is mathematically defined if we now have a continuous probability. So this would be defined as a probability for x only, which is then given by an integral over y over the domain of variables which define the stochastic variable y. And then we would have an integral over the y degrees of freedom. So that means that we are now tracing out or integrating out one of the variables. So this is a parallel to what we are doing here. So we have a quantity which depends on both system A and B, and we're now only interested in the properties of system A, or alternatively system B. So it's pretty similar to what we do when we calculate the marginal probability. And if some of you are familiar with machine learning, you may have encountered something called Boltzmann machines. And in Boltzmann machines, you have hidden variables. And at the end, you want to only have a probability distribution which represents, let's say, the x degrees of freedom, and you want to integrate away the hidden variables because they are not relevant for the quantity you want at the very end. So if we just want p of x, we would have to integrate away the other degrees of freedom. And then the question now is whether this rho of A represents a pure state or a mixed state. In our case, this is going to lead to a situation for the Bell states where the subsystem A is undefined in the sense that we cannot say whether the system is in qubit 0 in system A or in qubit 1. So let's now look at the mathematical detail on how we would actually do these operations. So we would have to convert the qubit 0 in the system into an object which has the right dimensions. So our vector is actually given by 1, 0. So this is the qubit 0 in system A. And then we are taking the tensor product with the identity matrix. Now this gives us a matrix which has dimensionality 4 times 2. So that means that what we are having now is this matrix, 0, 1, 0, 0. And then similarly, we would have a vector for the first qubit, qubits 1, which is then simply similar tensor product with qubit 1 multiplied with the identity matrix. And that gives us a new matrix, which is also 4 by 2 matrix, where we now have 0, 0, 0, 0, and then we have 1, 0, and 0, 1. So what we're doing next then is that if we now look at the 0A with row AB and 0A here, this is what we end up looking at. This is us now taking the following matrix products. So we would have 1, 0, 0, 0, and 0, 1, 0, 0, multiplied with the density matrix for the phi plus state, one of the Bell states, as we discussed earlier. And then we would have 1, 0, 0, 1. And this is then multiplied with 1, 0, 0, 1, 0, 0, 0, 0. And when we do the linear algebra then, we are going to get something which leads to, when we now take this into account, when we do the same for the 1A of row AB and 1A, this gives us, at the end, when we add everything, we find that the row of A is equal to, actually this is also equal to row B. You can easily see that one. This ends with 0, 0, the outer product of these guys, when we do the algebra here, of 1, 1 divided by 2. So if I square that quantity, if I take the row of A squared, what I will find then is that this is simply equal to 1/2, and take the trace of that. This is equal to 1/2, which is obviously less than 1. Now, this is a pretty remarkable result, because if I look at the state here, so the state of the joint system, which we started with, is a pure state. We know exactly how we have prepared the state. So the original state, this phi plus, which we defined, was given by a linear combination of 0, 0 plus 1, 1. So we call this a pure state. It's an entangled state, but it's a pure state because we can define it exactly from the very beginning. Now, when we now calculate the trace of the subsystem, so we are tracing out one of the degrees of freedom, what happens then is that even though we started with a pure state where it is known exactly, qubit A and qubit B, the two subsystems, are in what we call a mixed state. That is a state about which we apparently do not have maximal knowledge. And this is actually an important hallmark of entanglement. So we cannot say whether qubit 1 or qubit A in the system A is in state 0 or state 1. So what we see now is that when we take the trace of a pure state, so if we take the trace of the density matrix, for instance, for the state phi plus, we saw that that one is equal to 1. But when we, so this is a pure state, but if we take the trace of a state where the trace is less than 1, then, less than 1, sorry, but larger than 0 or equal to 0, then this is a so-called mixed state. So we can define exactly the two-body state in terms of an entangled state, which is a linear combination of 0, 0 plus 1, 1. But we cannot say whether the specific qubit in one of the subsystems is in the state of qubit 0 or qubit 1. And it's pretty easy to see also that the two density matrices are actually equal for the subsystems, and that the density matrix, so this is a density matrix for one of the subsystems, if we square this quantity here, we will now see that when we take the trace, that this trace is going to be equal to 1/2, which is obviously less than 1. So this is a typical definition which is being used for whether we have a mixed state or pure state. So the next quantity we want to discuss now is actually the entropy and its relation to density matrices, because that's going to provide us a way to measure whether the states are entangled or not. And the entropy is something which has been widely used in science and physics in particular. And we first start with the classical information entropy, and thereafter we switch to the quantum mechanical equivalent, which is normally known as the von Neumann entropy. And this is the quantity which we will use when we are going to analyze the system, and in particular the density matrix. So we're going to relate the density matrices to the entropy. Now, the classical entropy, when you now think of some of the basic ideas, so we want to have a function which expresses a measure of unlikelihood. So if we know which state we are in, which we know exactly what the probability is, then we want to find a measure for the degree of certainty and obviously the degree of uncertainty. So a typical example which we are going to look into is a binary system. So in the binary system, we know that we have for certain two states, either 0 and 1. So if it's in state 0, then we know that the probability is 1. And if it's in state 1, we also know that the probability has to be equal to 1. So the system is known precisely. So one simple measure then is actually to take the log of the probability. So that means that rare events, which have a very small probability, they will then carry a large information content. And certain events, which have probability 1, they carry 0 information. So that's just a way to find a possible representation of probabilities in terms of the degree of information content. So you can think of this quantity which we are searching for as a quantity which is now going to measure the degree of uncertainty in the system, or the uncertainty content. If we look at this specific function here, however, we see now that when the events are very rare and the probability goes to 0, this term here actually diverges. So what we would rather like to have is a quantity which does not diverge. And a possibility then is simply to multiply this function here with the probability itself. And that leads to a quantity which now, if we take in account random variables, we could then define a quantity here where we simply sum up over all the possible events which we have. This is a kind of a discrete random variable. And if we have a binary entropy, you could think of two possibilities. You have either probability P or 1 minus P. Now, if you look at the quantity which you have here, then you will see that this quantity here, when we know the probability, so if we are in the state P with certainty, that means 0 or 1, then this is exactly equal to 0. So that's max certainty. But then when we are in a mixed state, where the probability is equal to a half, then we have maximum uncertainty. So this is a pretty simple example on a kind of probability which we can obtain when we have a binary system. So if you were to plot that specific quantity, so let's just go back to the whiteboard then. If we take this binary case, which is a very simple case, so let's take a closer look at that one. So if we now look at this definition of entropy, we have a quantity which we define as H, and this is defined as minus sum from I equal 1 to 2. We have only two possibilities. So we have a probability P of I, and then we have a log of P of I. So what we also have is that we take the limb, you can actually show that when P goes to 0 of P of I, of log P of I, this goes actually to 0. Now, when we have this two possibilities, if we now replace the possibility with just a variable P, then we know that this quantity H for the binary system is given by minus P of log of P, and then I get minus, And then the other event is 1 minus p multiplied by log of 1 minus p. And we see immediately then that this entropy is equal to 0 if p is equal to 0, because if this variable p is equal to 0, the first term is 0, whereas the second term is also equal to 0 because we have log of 1, which is equal to 0. And if I take now the next case, if p is equal to 1, then we see also that we have log of 1 in the first term, which gives us 0. And then in the next term, we have 0 times log 0, which is equal to 0. So if I'm going to plot this quantity here as a function of this probability p, then this is what we would find when we make a simple plot of the system. So if we plot 1 here, we have h, and then we plot this as a function of p, and then we know that when it's 0, we are at 0. When it's 1, it's equal to 0 again. And then if I take the value of a half, this is when we have maximum uncertainty. This is when the entropy peaks. So that means that this quantity is going to look like this. So it peaks when we have maximum uncertainty, because then we have a 50-50 case. We don't know whether it's in the, let's say for the quantum mechanical case, it could be in qubit 0 or qubit 1. So this would be the case of max uncertainty. And that is when the entropy has its largest value. So it's an extremely useful way to quantify the degree of uncertainty. So in these cases here, on the other hand, we have what we might call max certainty. We know that we are either, when p is equal to 0, this could correspond to qubit 0, whereas when p is equal to 1, it could correspond to qubit 1. So that means that in those two cases, the system has collapsed to one of the states, and we know exactly in which state the system is. This is normally called the Shannon information entropy, and it simply gives us a measure of degree of uncertainty. Now, this means that we can define exactly the probabilities, and this applies to what we normally call classical probabilities. But when we are dealing with a quantum mechanical system, we have to make some small changes. And this is where the density matrix comes in and gives us a very useful way of calculating the entropy. And this entropy, which we are going to define, is the quantum mechanical variant of the Shannon entropy. And this is called the von Neumann entropy. I should also add that one of the other properties we want the entropy to have is that the entropy is additive. So if you have, for instance, two probabilities, suppose now your probability P of X of Y is given by the probability P of X. So this applies to the variable X. This is another probability which then acts only on Y. If we look at this quantity here, you can then easily see that if we take the log of these quantities of P of X and Y, this quantity is what we call additive, in the sense that this probability is simply going to be the probability of log of P of X plus the log of P of Y of Y. So in this case, we have assumed that we have identically and indistinguishable systems. So in this specific case, we see now that the entropies are additive, and this is another property which we want to have. So we could have taken, as we said, this quantity here minus log of P, but in that specific case, what we would have seen then, when we plot this as a function of P, when we move to 0, when P is going to 1, then obviously this converges to 0, but then it would diverge for very small probabilities. So in this case, the degree of uncertainty would be given by this diverging function. So normally it's not a feature we would like to have when we are going to define the degree of uncertainty. And that is why multiplying this with the probability self, the log, gives us something which peaks at the max uncertainty variable. So when we have a P equal to a half, which corresponds to a mixed situation, where we cannot tell whether we are in the state 0 and the state 1, then this gives us the max uncertainty. So it's a very useful and handy measure for the degree of uncertainty of the system. And we are going to then link the quantum mechanical object with the density matrix. So let's go back to these slides again. And then look at the quantum mechanical definition of probabilities and entropy. So this is just a quick repetition of what you saw on the whiteboard. And there is a simple, in the Jupyter notebook, you will also find a simple code which actually computes the binary case and computes the entropy for the binary case. So what we have done now is then simply with a set of random variables with probability out for an outcome X within the domain uppercase letter X, given by this probability, then the classical Shannon information entropy is just given by this quantity which we have. And just to repeat, the basic idea behind the classical entropy, when it's used as an information entropy, is that we want to have a measure of unlikelihood or uncertainty. And then for the binary system, this is essentially what we saw, that when P is equal to either 0 and 1, then we know exactly in which state the system is. Whereas when we have P equal to half, we are in a mixed situation. So let's just skip some of these because this is basically what we went through now. So the binary example is what we illustrated on the slide, on the whiteboard. So our lack of knowledge at the end is expressed by the largest entropy value. And when we come to the quantum entropy, what we now want to have is a measure of the degree of mixedness and pureness of the states. So when we have, just to quickly remind ourselves, when we have a pure state, then the density matrix squared is equal to the density matrix. Whereas when we have a mixed state, which means that we cannot tell whether the system is in that state or that state. And if you go back to the Bell states, we saw that when we traced out the subsystem and looked at subsystem A or subsystem B, we couldn't tell exactly whether the system was in qubit 0 or qubit 1. And in that specific case, we have that the trace is less than 1, the trace of the density matrix squared. And the properties of the density matrix, just to remind you of that, is a quantity which is positive definite, should have trace equal to 1. That's the density matrix itself, but not the squared. And it's also a emission quantity. So the quantum analog of the Shannon entropy is something which we are going to define as a quantity which is given by the probability. In our case, it's actually going to be given by the density matrix. And it's going to have the eigenvalues of the density matrix and the log of the eigenvalues. And now we're going to derive this equation here. So another thing which is very interesting is that the maximal dimension in the state which we have is now given if you think of the density matrix. So this is going to be encoded as the log 2 of the dimension. So you don't need to stay with a log 2 basis. This just gives us a scaling factor. So using density matrix, we are going to define the quantum mechanical equivalent of the classical entropy as the negative trace of the density matrix times log 2 of the density matrix. And this is called the von Neumann entropy. So the question is, how do we actually get to this expression? So you could simply take the point of view that, okay, I'm just going to use this quantity as a way to define my degree of uncertainty. So, and the higher the degree of uncertainty, the more entangled the system is. And why can't we use the classical definition for quantum mechanical system as well? Now, the problem with a quantum mechanical system is that the states we are looking at are normally a linear combination in terms of a computational basis. And in our case, the computational basis is given by the states of a quantum mechanical system. So let us remind ourselves a little bit about the density matrix. So the density matrix, when you have an orthogonal basis, this is the basis we have, is then given in terms of the probabilities of being in that state, which are just the overlap coefficients. And these overlap coefficients are then the eigenvalues of the density matrix. So keep again, note again that this is important for the derivations which are coming, is that the density matrix is actually a semi-positive definite matrix, which means that all the eigenvalues are larger or equal than 0. Now, and now comes some elements of linear algebra. So what we have first is that suppose now you perform a unitary transformation. That means, because the density matrix, just remember that the density matrix is not necessarily diagonal, but we can transform it into diagonal form by finding an appropriate unitary transformation. So that means that when we do that, we would then get a transform matrix which is diagonal, and where these probabilities of the overlap coefficients are those which are along the diagonals, because these are the eigenvalues of the density matrix. Remember also that when you perform a unitary transformation or an orthogonal transformation, a similarity transformation like this one, where you keep the same dimensions of the matrices and you get a diagonal matrix, the eigenvalues are conserved. They do not change when we perform a unitary transformation. So if I now look at the object which I construct with an equivalent of the classical Shannon entropy, we are now going to compute rho of A, the density matrix for this system A, and take the log of the system. Then we recall that the unitary transformations have to obey this relation here. So that means that if I now take the unitary transformation, or actually a similarity transformation is more correct, of this object, I can now insert an identity matrix here. And then you see now that if I insert an identity matrix here, I will have U emission conjugate, rho of A times U. So that term becomes equal to that matrix. But then I'm left with a U emission conjugate here, multiplied with the log of the matrix here. Now this matrix is diagonal. So what I can do now is simply to define that object. You can actually show that this is the case if I do that transformation, because this is actually log 2 of D of A. Then what you have is that you can rewrite the density matrix in terms of a diagonal matrix times the log 2 of a diagonal matrix. Now the question is, if you now look at this quantity here, so what we would have then is that the log of D of A, this diagonal matrix, is simply given by the probability, log of the probabilities here. Now, if we then take the trace of this quantity, which is equivalent with this one, this is nothing but the trace of the diagonal elements times the log of D of A. So the log of this matrix is simply given by this quantity. So if we use that one, we can simply rewrite that one as the probabilities. So these are the eigenvalues of the density matrix, times the log of the probabilities. And that allows us to define the general von Neumann entropy as the negative trace of the density matrix of the log 2 of the density matrix. And then performing a unitary transformation gives the expression we know from classical information. So this will be the starting point, the equation which you see here. And this translates into the final result, which is something which is pretty close to the classical expression from the Shannon information entropy. So if we now go back to the Jupyter notebook, and this is where we will end the lecture today. So let's take a quick look at that one. Then we can calculate and show how you can calculate the density matrices and the von Neumann entropy. So let's just bring that up here. So the first case which you see here was actually a calculation of the classical probability. And if you take that one, you see now that you have roughly 0 when p is equal to 0, and 0 when it's 1. And then it peaks at 0.5, which is the maximum uncertainty. So if we now scroll down here a little bit and look at the code which we have set up, this code simply calculates the density matrix and the von Neumann entropy of a simple case. So we have the outer product for a state vector of length 4. So this will be the typical case which we have for the computational basis. And then here we perform the partial trace over qubit B for a 2-qubit density matrix. So this goes back to the equations which we saw previously, where we now have calculated the, let's say, state like the Bell state, or we could take any linear combination of these states or just calculate the 0, 0 states. And then we trace out in here, we are performing the tracing out of the subsystem. And then we can actually, with that one, we can calculate the eigenvalues of a 2 by 2 matrix. And calculate that one, we can then calculate the von Neumann entropy. So we started with a state which is given by 2 qubits. We set up the density matrix for that specific system. Then we calculate the eigenvalues, and then we have the probabilities. So the eigenvalues of the density matrix. So this density matrix, which we get here, is now a 2 by 2 matrix. And if we run these calculations here, we will then see that the von Neumann entropy for this specific case, when we start with a 0, 0 or 1, 1, etc., this just gives us equal to 1 here. So this is the state when we have a linear combination for a Bell state, which then gives us a maximum entropy of equal to 1 here. And then what you will also find in the lecture notes here is an example of a pure Python code, which just a plain Python code without using any libraries except the NumPy or similar libraries. There is no Qiskit. This is something which we will start discussing next week. This code here gives you also an example on how you can set up a measurement. And in this specific case, we are having a projection operator, which is now given by this specific qubit state, which we are interested in, times the identity matrix, so that we get the right dimensionality. And then the post-measurement state is simply given by this operator P of k, which projects out one of the states, acting on the original state, and divided by the norm here, so that we have a normalized state. And below, we compute P of 0 and P of 1, and the conditional post-measurement state vectors. So this is also an example of something which we will use in the first project as well. So this is a case where we have a qubit A, which we want to measure in a computational basis on a 2-qubit state vector. And the outcome is either 0 and 1. So I invite you to take a look at these codes and simply then run the codes and see how they're set up. And you can see now that in this specific case, we have a post state where we simply have the 0, 0 state. This is this one. And that gives us a probability of a half. And then if I do the measurement P of 1, so I'm starting with one of these Bell states. So all the operations which you're seeing here are actually the Bell states. And then we have a post state which is now equal to the 1, 1 state here. And then there's also an example here where you can calculate the von Neumann entropy from eigenvalues of a 2 by 2 matrix. And as I said, I invite you to take a look at these states here. And there's also an example here on you can build the Bell states and compute the entanglement entropy. But this is something which we will discuss in a little bit more detail next week when we are going to look at how we can set up the Bell states. So again, these are codes where we set up first the outer product, as you can see here. We trace, do the partial trace over system B, and then we have an entangled states. And when we start with the Bell states as a length 4 vector, so you can see that this is now given by the phi plus is the state which we discussed, which is just 1 times 1 over square root of 2. And then we have 0, 0, and 1. And then we can calculate the entropy for one of these specific states. And then the expected output is eigenvalues of 1/2 and 1/2, and the entropy 1 for all the Bell states, as expected. So if you, oops, there's a traceback here which didn't run properly. Okay, so I have to rerun some of the states here. I didn't run this one. So let's just rerun that one. And now it runs. I forgot to run one of the codes first. And as you can see now, the eigenvalues are given by 1/2, as obviously, as expected. And then we have that the max entropy or the entropy for the states is equal to 1. So this is a typical example when we now trace out the subsystem where we have the high level of uncertainty. We don't know whether the specific traced out subsystem is in state of qubit 0 or qubit 1. Now, there are some further examples which I invite you to take a look at, where we have a partially entangled state, which is given by cosine theta plus some sine theta. This is going to turn pretty useful when we are going to look at the examples in project number 1, some of the exercises, because in a variational quantum circuit, we are going to have variational parameters expressed by rotation angles. And this is a typical example of a way which you could obtain an entangled state. And we are going to discuss that a little bit later. And here you have examples where you also use NumPy. And I invite you to take a look at these because these are exercises which we'll also deal with next week. So if we want to summarize, the Shannon entropy measures the classical uncertainty. The von Neumann entropy measures quantum mixedness. And for a pure bipartite state, this quantity here, when we have traced out, quantifies entanglement. So it's a measure of entanglement. And Bell states have reduced matrix density matrices, which are given by the identity matrix divided by 2. When we square that one, that is going to give us a trace which is less than 1. And it has an entanglement entropy which is equal to 1. So that means that we have maximum degree of uncertainty. So I invite you to take a look at the exercises and also the codes here, because this is something which we are going to use again in the first project. So the plan for next week is actually to have a quick summary of these discussions of entanglements and the measures of entanglements. And we're going to link that with a Schmidt decomposition. And then we're going to introduce 1 and 2 qubit gates and simple Hamiltonians. And these simple Hamiltonians, which are then going to be given by 2 by 2 matrices, which we can diagonalize analytically easily, and a 2 by 2 qubit system, which is going to lead to a 4 by 4 matrix, which we also can set up and calculate the eigenvalues of, both numerically easily, but we are going to calculate the eigenvalues with the variational quantum eigensolvers. And then we are going to discuss a little bit more codes, and there's also going to be a short introduction to Qiskit. And everything which we will discuss next week is linked with the project. And the final version of the project will be presented next week. So this ends the lecture this week, and best wishes to everybody.